So this is problem 713 on Hibbeler's book. And in this problem, we want to find the internal forces, that is the normal and the shear force, and the internal bending moment at points D and E in the system. In the figure, point D is located just to the left of the 5 kip load. Now, I haven't really used kips in class that much, but a kip is essentially a kilopound, so 1,000 pounds. But it's okay, we're going to express all of our force dimensions in kips here. In order to solve this problem, this is an internal forces problem, so I would say the first step would be to draw a free body diagram. Now, the figure here, the system here, has two members. It has member AB, and that is connected to member BC. So when we're drawing a free body diagram, we're going to have to choose which one of these two members to use. Now, the purpose of drawing the free body diagram is to find the reaction forces. C already has 3 reaction forces: a force in the x direction, a reaction in the y direction, and a moment. However, A, which is a roller, only has a reaction in the normal direction to the surface, which is the y direction. So I'm going to choose my member AB in order to find my reaction forces at A, and that will also help me find the forces at the hinge. I'm going to call my reaction at the roller AY, and since B is a hinge, it's going to have a Y and an X component for the reaction. I'm going to call my Y reaction BY, and I'm going to call my X reaction BX. We're not really sure the directions of these reaction forces, so I can just assume the directions that I drew. In this member, I have an external force of 5 kips acting at the center, and I have a moment of 6 kip feet. I think that's all we need for our free body diagram. It would be helpful to write down some dimensions. So from point A to those 5 kips, we have 6 feet. And from those 5 kips to point B, we have another 6 feet. So that is my free body diagram. Now, the reason I draw this free body diagram is because I want to solve for the reactions. So now I want to find my reactions at A and at B. If I were to take my sum of forces in the y direction, I would end up with 2 unknowns, AY and BY. So it's best not to start with that. Instead, we're going to start by taking the sum of moments about point A. So my sum of moments about point A should equal 0. And if I look at point A, I will have a 6 kip times feet moment, causing a counterclockwise rotation, so we're going to keep it positive. I'm going to have a 5 kip load acting at 6 feet from the point. Which would cause a clockwise rotation, so I'll assign it a negative value. And I'm going to have my unknown reaction force By acting at a distance of 12 feet. This would cause a counterclockwise rotation, so I'm going to give it a positive sign. Those are all the moments acting about point A, so I'm going to set all of these as equal to 0, to satisfy the equations of equilibrium. Now we can solve for By, which should be equal to 5 times 6 kip feet minus 6 kip feet divided by 12. This gives us a total of 2 kips. So I found By. Now that I found By, I can find Ay. Now, since I will only have one unknown in the y direction, I can easily just take my sum of forces in the y-axis. An alternative would be to take the sum of moments about point B. Either option will give me the correct answer. So just to get a little bit of practice, I'm going to take the sum of moments about point B. Now looking at this, we are going to have a 6 kip times feet moment causing a counterclockwise rotation. I'm going to have a 5 kip load acting at 6 feet from point B causing a counterclockwise rotation, so this time it will be positive. And I will have an unknown AY vertical force at a distance of 12 feet from point B causing a negative moment. Solving for AY, this will give us a force equal to 6 kip feet plus 5 times 6 kip feet divided by 12, or just 3 kips. Notice that we could have done this by just taking the sum of forces in the y direction. In the y direction, we would have had our unknown AY plus a force of 2 kips minus a force of 5 kips equals 0, which again would give us AY equals 5 minus 2, or just 3 kips. Our reaction in the x direction can be found by taking the sum of forces in the x direction. And in this case, we only have one force acting in the x direction, and that's our unknown Bx, which means that Bx will be equal to 0. So now that I've found all my reaction forces, I can create my cut in order to find the internal forces at my point of interest. In this case, we want to find our internal forces at 2 points, points D and E. I'm going to start with point D since we already have a free body diagram drawn for that point. We're told that point D is located at immediately to the left of the 5 kip load. However, because it's immediately to the left, the distance from that point to our roller A is still going to be 6 feet. So when I make my cut, I want my cut to go through point D. However, keeping in mind that it is immediately to the left of the 5 kip force. So that's what my cut will look like. And after making this cut, I can discard the right section. My new cut section will look like this. Where I have a force of AY of 3 kips, a moment of 6 kip times feet, and we're not going to include the 5 kips load because the point D is located directly before the 5 kip load. However, we do have to consider our internal forces. We're going to have a normal force, a shear force, and a bending moment. I'm going to assume that all three load internal forces are positive for now. We can find all of our internal forces now by applying the equations of equilibrium. So applying the equations of equilibrium to this section, section AD, will yield the following. Taking the sum of forces in the x direction, we can find that the unknown normal force at point D is equal to 0. Taking the sum of forces in the y direction, we will find that the unknown shear force will have the same magnitude as the 3 kips reaction from the roller. And now, taking the sum of moments about point D, we'll find that the moment, unknown moment at point D plus the 6 kips times feet and minus, because we need to consider this force as well, minus the 3 kips that are acting at a distance of 6 feet from the point, should be equal to 0. We can now solve for our unknown bending moment, which should be equal to 18 kip feet minus 6 kip feet, or just 12 kips times feet. So we found our internal forces at point D. Notice that we only needed one section to find these internal forces. So there was no need to calculate the reactions on the right side of the system. We're going to find that in order to find the forces at point E, we still don't need to calculate these reactions. So in order to find our internal forces at point E, we need to go back to step number 3 and repeat it, which is to make a cut. In this case, I want my cut to go through point E, so I'm going to cut my system around here. However, I already know my hinge reactions at B, which means that I only need to consider the section of this member that goes from B to E. So if I were to draw a free body diagram, it would look like this. On my member AB, my hinge reaction was positive, pointing upwards. That is because applying these forces would have caused this member, to experience a force pushing upwards to keep it balanced. Since this member BC, is connected to AB, the force that the hinge will experience at BC is going to have the opposite direction than the force that the member experiences at AB. This is because both hinge forces from both members have to cancel out in order for the system to be in equilibrium. Therefore, when I draw my free body diagram for member BC from B to E, my reaction force at the hinge will have the opposite direction, so it will be pointing downwards. I also have a distributed load of 1.5 kips per feet. And this goes from point B to point E, which is located at a distance of 4 feet from point B. Since I made my cut at point E and I want to find my internal forces at point D, I'm going to start by assuming that all of my internal forces have positive directions. And now I can apply my equations of equilibrium to solve this problem. I can start by my sum of forces in the x direction to find that the normal force at point E is equal to 0. Then I can take my sum of forces in the y direction. In the y direction, I'm going to have a negative 2 kip force downward, and I will also have the resultant from this distributed load. We can reduce this distributed load into one point force by taking the area of this distribution. In this case, since this is a rectangular load, the area will be equal to the base, which is 4 feet, times the magnitude of the distributed load, which is 1.5 kips per feet. And pointing downward. Notice that feet will cancel out with feet. Finally, I will have my shear force, also pointing downward. Now I can solve for my unknown shear force. In this case, my shear force will be equal to -2 minus 1.5 times 4. In other words, my shear force is equal to -8 kips. What does that negative signify? That means that the direction that I assumed for the internal shear force is incorrect. Since we're using this as our standard sign convention for internal forces, leaving this answer as -8 should be fine. Finally, I want to find my internal bending moment at point E. I do this by taking the sum of moments about point E. In this case, I have my internal bending moment, and since it's acting counterclockwise, I'm going to give it a positive sign. I also have the distributed load. The moment of the distributed load can be found by reducing the load into one point force, which is what we did in this step, and then multiplying it by the distance from the point to the centroid of this distribution. So I'm going to take the reduced load first. Feet cancels out with feet, but this still leaves us with only a kip value. The distance from point E to the centroid can be found by first locating the centroid of this distribution. This is a rectangular distribution, so the centroid will be at the center of that distribution, and the distance from this point to the centroid will be equal to half of 4 feet, or just 2 feet. Moment will be counterclockwise, so I'm going to assign it a positive value. I also need to consider the moment caused by these 2 kips that come from the hinge. The 2 kips are acting at a distance of 4 feet from point E and are causing a counterclockwise moment, so I will give it a positive sign. Now I can go ahead and solve for my unknown internal bending moment, ME. my internal bending moment, ME, should be equal to negative 1.5 times 4 times 2 minus 2 times 4, or just negative 20 kips times foot. This negative tells us that the assumed direction of the internal moment was incorrect. In other words, both the shear force and the bending moment are acting in the opposite directions than that we drew.